Hello everyone, and welcome back. I wanted to make a quick video talking about two special rules in momentum that tend to rear their ugly heads every now and then. Now these are pretty rare, but I wanted to talk about them just in case. And to start out, here's how you recognize that these may come into play. If you are ever given an obvious collision, but you are not given the masses, or if they want to be really tricky and they only give you one of the masses, I want you to think about these two rules. Basically, they come into play if it looks like you're not given enough information to solve the problem. And in truth, that's kind of the point. So the first one has to deal with 2D collisions. And here's the rule. If one object collides with another object at rest that is the same mass, then the two objects will separate from each other at a 90-degree angle. As a side note, this only comes into play if the objects are round or will bounce off each other in a similar way. So let's say these are two billiard balls, because this rule actually does come into play in the billiard table quite often. Or we can say these are protons. Those are actually the two most common examples used in problems. So let's say this yellow ball hits this purple one, and the purple ball flies off at an angle of 20 degrees below the positive x-axis. You are asked, in what direction will the yellow ball go? Well, if they separate at a 90-degree angle, then the yellow ball is going to go this way. And if this is 20 degrees, this is going to be 70 degrees. So it would be 70 degrees above the positive x-axis. Again, very rare, but it does come up every now and then. The other rule has to do with elastic collisions. An elastic collision is a special case because both momentum and kinetic energy are conserved. This means that you can solve for two missing variables. So I'm going to skip the derivation because it's long and boring, but it really comes down to this. And this is a single axis situation. Basically what this is saying is the combined velocity at which the two objects are moving toward each other after the hit equals the combined velocity of the two objects moving away from each other. Let me show you a quick example of this. Okay, so let's say we have this situation. Card A moves to the right with a velocity of 3 meters a second and collides with card B, which is moving to the left at 2 meters a second. After the elastic collision, card A is moving to the left at 1 meters per second. What is the final velocity of card B? Now you notice we are missing both masses and we're missing the final velocity of card B. So there are a lot of things that are not given to you. That's your big hint here. They specifically mention it's also an elastic collision, which means you can use a special rule. And on the bottom here, I put both equations. The momentum collision equation, which is always true, and the equation for a special case here. Now with this level problem, it could basically be done two ways. First, these two cars are coming at each other with a combined velocity of 5 meters per second. Therefore, they're going to leave each other with a combined velocity of 5 meters a second, which means this is moving to the left at 1 meter a second, which means this one should end up moving to the right at 4 meters per second. 5 meters a second toward each other, 5 meters a second away from each other. But let's double check that. I will take this equation. I'm going to factor in that negative sign. 3 meters a second minus negative 2 meters a second equals negative 1 meter a second plus VB final. I will get 3 plus 2 equals 5 meters a second minus negative 1 meters per second because object A is moving to the left plus VB final. 3 meters a second plus 2 meters a second gives me 5. This will be a positive, but then I subtract it from the other side, which gives me 4 meters per second equals VB final. So questions like this come up on the multi-choice part of the AP exam every now and then, because you can obviously do this math in under a minute. All right, let's try one that's a little more complicated. If a ball of mass 0.44 kilograms moving along the positive x-axis with a speed of 3.3 meters a second collides head-on with a 0.22 kilogram ball at rest, if the collision is perfectly elastic, what will be the speed and direction of each ball after the collision? So flat out, they're telling you have two unknowns. Let's start by listing givens. Mass A, 0.44 kilograms. Mass B, 0.22 kilograms. Velocity A initial, 3.3 meters a second. Velocity B initial is 0. And velocity A final, velocity B final are both unknowns. I'm going to start with our new equation. Again, I'm going to factor in the negative. 3.3 meters a second minus 0. Nothing changes to the right side. I'm going to rearrange this to solve for VB final, which gives me VB final equals VA final plus 3.3 meters a second. I'm going to move over to my momentum equation. Immediately, there's no VBI. 0.44 kilograms times 3.3 meters a second equals 0.4 kilograms times VA final plus 0.22 kilograms. Now I'm going to do a substitution here. Since VB final equals this, I'm going to take this and substitute it in over here, which gives me VA final plus 3.3 meters per second. Now in this equation, I only have one unknown, which is VA final. Let's do some rearranging. 1.452 kgm of rest. This stays. Plus 0.22 kilograms times VA final. Plus 0.726 kgm of rest. Let's neaten this up a little bit. 0.726 kgm of rest equals 0.66 kilograms times VA final. That gives me a VA final of positive 1.1 meters per second when I divide out the masses. So here's my final answer for velocity A final. Now I just take this, plug it back into here. I get velocity B final is 1.1 meters per second plus 2.3 meters per second. So velocity V final is 4.4 meters per second. So this was solving a collision situation with two unknowns. And this can only be done if the collision is on a single axis and is an elastic collision. Again, both of these special rules are pretty rare, but you will recognize them if it looks like you are not given enough information, particularly if you are not given the masses. So hopefully you will never have to use these, but just in case, I do hope it will help you out. Have a good day. This is Mr. M signing off.